Okay, let's talk about the boiling point elevation. The formula, which you can see here, depicts the change in the boiling point temperature of the solution as compared to the pure solvent. And in this formula, we actually have the number of ions integrated in the formula itself. So we don't need to calculate how many ions there are in case the substance is ionic. If the substance is covalent, then I is automatically 1. Alright, so here we have 5 grams of lithium chloride, which we're going to dissolve in 50 ml of methanol. And we want to find out what happens to the boiling point of this solution, or what the final boiling point ends up being. Now in the formula, we do need the molality. So we're going to need the moles of the solute, and we're going to need the kilograms of the solvent. So the moles of the solute is simply taken by dividing the 5 grams of lithium chloride with its molar mass, 42.39 grams per mole. This yields the moles of lithium chloride. Now for the solvent methanol, we take the mLs of methanol, multiply them by the density of methanol, 0.792 grams per ml, cancel out the mLs. And since we need kilograms of solvent, here you just want to divide this by 1000 grams, which is equal to 1 kilogram of solvent. This will provide you with the kilograms. Now you can calculate the molality. Okay, in order to do that, we divide the 0.118 moles of solute by the 0.039 kilograms of solvent, and it should be 0.0396 kilograms. In this case, we're talking about a molality of 3.03. And now finally we use the equation. The change in the boiling point will be given by I, which in the case of lithium chloride corresponds to 2 ions, one for lithium, one for chloride, so 2 ions. The Kb constant needs to be given, and that's shown right here, 2.7 degrees Celsius per molality, and the molality is 3.03. So molality cancels out, and you end up with only degrees Celsius, in this case 16.36 degrees Celsius. Alright, now what I need to reiterate and make sure that it's completely clear is that when you get this value, this is not the final answer. This is the change in temperature of the boiling point. The boiling point itself is going to be the value that we got here, the delta T boiling, plus the original boiling point of the substance. Hence the fact that this is boiling point elevation, because you are elevating the boiling point, you're raising it. So you will literally add it up to the boiling point of the pure liquid. And you see here the boiling point of methanol is 72.2 by itself. With this molality, we're going to raise the boiling point by 16.36, meaning that the actual boiling point is 88.56 or 88.6. Alright, so that's the boiling point elevation. Let's take a look at the freezing point depression, since it bears a similar approach. The formula, as you can see, is exactly the same, except that now we use the freezing point constant, and now we're looking at the freezing point depression, meaning that we're going to be lower in temperature at the end. Okay, so here I changed things a little bit. We have half a gram of lithium chloride dissolving in 50 ml of ethanol, not methanol. We have the density of ethanol, the molar weight of ethanol, and the vapor pressure, although we don't need the vapor pressure here, but we have the melting point, that's the important thing, and the freezing point constant. Alright, so we take the 0.5 grams of lithium chloride and we change into moles using the molar mass. We get the 0.012 moles of lithium chloride. Next, the 50 ml of ethanol can multiply by the 0.789 grams per ml of ethanol in order to switch over to mass. And remember, we're going after the molality, so we need to change this to kilograms of solvent. So we divide by 1000 in order to end up with kilograms. So here we're dealing with 0.0394 kilograms of solvent. Dividing the solute moles by the solvent mass in kilograms ends up yielding 0.305 molal. Okay, now we use the formula. The freezing point change in temperature is given by IKFM. Kf given in the problem itself is 2 degrees Celsius per molal. The value of I, since this is lithium chloride, is 2 because we have 2 ions present, and the molality is 0.305. So the change in temperature is 1.647. Once again, this is not the answer, this is the change in the melting point. Since this is freezing point depression, what we need to do is look at the melting point, negative 114.6, and simply subtract this value from it. That subtraction will give you a lower number, in this case negative 116.2 degrees Celsius, as the melting point of the substance. So just remember, delta T stands for the change, not the actual boiling point or melting point of the substance. Alright, finally, osmotic pressure. This actually uses molarity as the concentration unit. And on top of that, we're going to be using the gas constant 0.08206, since we'll be talking about pressure. Alright, now osmotic pressure, as I mentioned earlier, has to do with placing two solutions next to each other. They're actually separated by a membrane, but the membrane allows the solvent to travel through either side of the compartment. The solid particles, however, remain stuck in the compartment there originally. Now the idea right here is kind of similar to the zeroth law of thermodynamics, namely that you want an equilibration to take place. The concentration on the left side of the equation is lower on the left side than it is on the right side. So what ends up happening is that because the membrane here is permeable to the solvent will move from left to right in order to increase the concentration on the left side of the compartment and decrease the concentration on the right side of the compartment. In other words, the solvent flows from the low concentration area to the high concentration area. Alright, so as I was depicting, yes, we have this concentration change or movement from low concentration to high concentration for the solvent. And because of that, you end up creating more pressure on the compartment here on the right. This is what we call the osmotic pressure. And this actually has many specific aspects or examples in nature where it shows up. One of them is in regards to the red blood cells. Here on the left side of the graph, you see normal, regular red blood cells, with typical shape. But then you have cells that have been basically exposed to plasma, which is basically the fluid from which they are flowing into, which is either low in concentration or high in concentration in respect to certain solids. So you can see here, how the cells change in formula. These ones have been basically left with very little water inside of them because the concentration outside ended up being very, very high. So the water from the cells, from the inside of the cells, exited them out in order to try to lower the concentration outside of the cells. And over here, the opposite end takes place. The cells are placed in a solution that is very low in concentration outside of them, and so the water from the outside rushes into the inside of the cell, making them all puffy and globular. In some cases, this could be so extreme that the cells may actually explode. They might actually just like burst. And this is one of the reasons why they tell you, don't drink water that is low in electrolytes, because you will decrease the concentration outside of the cells and you could end up with this type of problems. At the same time, osmotic pressure helps other types of living organisms grow and become mature, such as trees. Trees use this idea of osmotic pressure to basically extend their branches. The branches that extend out of the trees is all a result of osmotic pressure, simply by having compartments with different values of concentration that allow the water to flow freely from compartment to compartment. Alright, so yeah, here are a few extra pictures of the cells in hypertonic and hypotonic solutions. So it's kind of an interesting approach. Alright, let's calculate the osmotic pressure. Here we have a non-electrolyte solute, meaning that the solute is not ionic. So we have a covalent solute, which means that the value of I will be 1. We know the pressure in human blood to be 7.53 atmospheres and the temperature of the body to be 37 degrees Celsius. So we want to find out what type of osmotic pressure this will correspond to. So we use the osmotic pressure formula, and here we're solving for the concentration of this electrolyte solute. So we solve for M. So we divide by I RT, and the osmotic pressure we're being told is 7.53 atmospheres. The temperature is 37 degrees Celsius. Make sure to change that to Kelvin. So 310 Kelvin is really what you have. And you input the value of R, which is 0.08206 atmosphere liter mole Kelvin. If you accidentally input 8.3145, the answer will be automatically incorrect. The value of I, as I depicted, is already 1 because this is a non-electrolyte solute, not ionic. So your atmospheres cancel out, your Kelvin cancel out, and you end up with moles per liter, which are the units of molarity. So this is how you go about finding molarity. But you could also use this to find the actual osmotic pressure of the sample. You could even use this to find ultimately the moles of the sample and even the molar mass of the sample. So just be aware of those little derivations that can happen. But with this, we're basically done. This is the last lecture to be covered, and it is the last thing that we'll encounter on the final exam. So, I hope you liked and enjoyed this set of lectures. I know we had some interesting circumstances this semester, but all that being said, I hope you enjoy these lectures. It's been a pleasure teaching you, and I hope to see you in the future. And if not, I wish you the best of luck in all your academic endeavors. Thank you.